Lecture 3, Ice Ages and Beyond. In the first lecture, we looked at the 150-year temperature record from thermometers and saw that Earth has indeed been warming, especially in recent decades. In the second lecture, we looked at a number of so-called fingerprints, other phenomena that also are indicative that Earth's climate is changing, either because temperature is rising or because other climate-related phenomena like species ranges and so on, melting of ice, are occurring. But we'd really like to know whether that roughly 150-year record of temperature corroborated by these other phenomena is just a natural occurrence in the history of Earth's climate, or whether there's something abnormal, something unusual, particularly about the warming of recent decades. So what we need to do to answer that question is somehow to go back further than the 150-year time horizon where we have enough data from thermometers to tell us something about Earth's global temperature. The problem is, of course, we don't have thermometers that were in enough quantity before about 1850, spread enough around the globe to measure an average global temperature. And if by a few hundred years before that, we don't have any kind of temperature measuring instruments at all. So how do we get back further? We've got to do that if we're going to find out whether the climate change we're seeing now is in fact something unusual or something just to be expected in the history of the planet. Well, what we have to do are to find measurements that serve as so-called proxies for temperature. Other things that we can measure that kind of stand in for temperature. Sometimes they may also stand in for other aspects of climate or other phenomena altogether, but at least they have to be able to give us some indication of what temperatures we're doing at times back before that historical temperature record. And it would be really nice if these proxy temperature measures also extended into the region where we have thermometer temperature measurements, because then we could cross-correlate them and understand them. So what are some of these proxies we use to go further back in time and try to establish so-called paleoclimate, climate in ancient times, or even climate in fairly recent centuries? What do we use? Well, there are a number of common proxies. One of them are tree rings. The oldest trees go back thousands of years. The rings in trees, the annual growth rings, tell us a lot of things. They tell us about conditions when the plant was growing. They tell us about temperature. They tell us about the length of the growing season. They tell us about humidity. They tell us about where the tree is in its age cycle, and all these things have to be sorted out. But if you look at tree rings, you look at the interior structure of a tree that's been sawed in half, you see these annual growth rings laid down as the tree undergoes its annual spurts of growth. The rings vary in thickness, they vary in density of wood, they vary in other quantities that tell us something about climatic conditions during the years that tree was growing. And because tree rings are laid down annually, we have a precise measure of when a given tree ring is associated with, and therefore we have a real datable record of past climate as measured by tree rings. Now, tree rings are most useful in regions like the temperate zones where there are large summer-winter temperature differences. Tree rings in the tropics aren't going to tell you a lot, but tree rings in the temperate climate where there's this large differential between summer and winter tell you quite a bit about the climatic conditions at that kind. If you go into the tropical oceans, you find, in contrast, coral reefs. And coral reefs form annual layers of the calcium carbonate, which is what forms the shell structure of shelled marine organisms. And analysis of those layers tell you something about the temperature of the water at the time the coral reefs were forming. So coral reefs are analogous in some sense to tree rings, except they work for warm tropical waters, whereas tree rings tend to work for temperate land areas. So they're complementary in that sense. We can get at two different regions of the planet by looking at tree rings and looking at coral reefs. Lake sediments. Freshwater lakes have layers of sediment typically on the bottom. Where do those sediments come from? Well, they come from streams that are washing the sediment in. There tends to be a lot of stream flow in the spring when there's snowmelt going on, and then as the summer progresses, the stream flow dies down. Sometimes it goes away altogether, and as a result of that, the sediments in freshwater lakes tend to be deposited in layers, which you can, again, as with tree rings or coral reefs, identify on a year-to-year basis. You actually look at the sediments, you take a core of them, and you can see individual layers. And the thickness of those layers tells you something about the intensity of the snowmelt. They tell you how rapidly the streams were flowing. They tell you a measure of the springtime temperatures, roughly. Also, in those sediments, one often finds pollens. And if one goes back long distances in time, then those pollens tell you something about what kinds of species happen to be living in the surrounding land. And so lake sediments provide another proxy indicator of climate. But perhaps the most significant one, and the one that's going to take a little bit more scientific explanation here, are so-called isotope ratios. And I need to get a little tiny bit into nuclear physics here. I talked about some of this in my course, Physics in Your Life, and I'm going to talk about it again a little bit here. What is an isotope? Well, an isotope is one particular version of a chemical element. What's a chemical element? A chemical element is a substance characterized by a particular atom, and in particular, it's the number of protons, the positively charged subatomic particles that make up atomic nuclei along with neutrons, that determines what kind of a chemical element something is. And the reason the protons determine that is the protons are electrically charged, positive. They attract an equal number of electrons to complete the atom, the electrons orbiting around the nucleus in the simple classical picture of an atom. And it's that number of electrons, particularly the outermost electrons and their configuration, that determines the chemical behavior of the atom. And so the individual chemical elements and their very different chemical behaviors, for example, oxygen versus hydrogen versus gold versus uranium, those different chemical properties are determined by the number of protons in the atomic nucleus. The number of neutrons doesn't affect the chemical properties because neutrons are electrically neutral. And so you can have different so-called isotopes of the same element that have different numbers of neutrons but the same number of protons. And chemically, they're essentially indistinguishable. Two isotopes of oxygen are both oxygen. You can breathe chemical oxygen with either isotope and it will work pretty much the same in your system, for example. But the two isotopes differ, and they differ in mass, because an isotope with more neutrons is heavier. And so their physical properties are slightly, typically not dramatically, but slightly different. And that's what isotopes are. And I want to look in the context of this course and temperature proxies, particularly at isotopes of hydrogen and oxygen. Hydrogen, a very common element, component of water, normally consists of just a single proton. It's the simplest element. It's one proton in its nucleus surrounded by one electron. That's what hydrogen is. But there are two other isotopes of hydrogen. One is called deuterium. Its nucleus consists of a single proton. That's what makes it hydrogen. One positive electric charge, but also one neutron. And because a neutron and a proton weigh about the same, in fact, deuterium is about twice as heavy as ordinary hydrogen. And deuterium is a stable isotope, which means it can exist basically forever. And there is some deuterium among the hydrogen here on Earth and elsewhere in the universe. And in fact, about 1 out of roughly every 6,500 hydrogen atoms is in fact deuterium. It's also called H2 because it's got two nucleons, two either neutrons or protons in its nucleus. So there's deuterium, and it is twice as heavy as hydrogen, although there isn't very much of it. Oxygen, another common material on Earth, in fact, the most abundant material in Earth's crust is oxygen, comes commonly in the isotope oxygen-16. Oxygen has 8 protons in its nucleus. Any nucleus with 8 protons is oxygen. It's got 8 electrons surrounding it to make an atom, and that determines its chemistry. Most oxygen is oxygen-16, but a small amount of oxygen is oxygen-18. Oxygen-18 has 2 extra neutrons. There's also oxygen-17. There's also, by the way, hydrogen-3, but that's radioactive, so it doesn't tend to hang around. But the oxygen isotopes, 16, 17, and 18, are stable. They can exist basically forever. And 16 and 18 are particularly significant in trying to measure temperatures, as are the hydrogen isotopes, hydrogen and deuterium. So what's the deal? How do we figure out what temperatures have been based on these isotope ratios? Well, there are a number of ways we do it depending on what we're looking at. And I want to focus on looking at ice cores. Because in the Arctic and Antarctic, we can drill into ice sheets that are a mile or so thick. And again, the ice tends to form in layers associated with the annual snowfall, and sometimes we can see individual years in the ice core record, and other times those are kind of smeared together and the dating is a little bit more approximate. But in any event, we can go back in these ice cores and we can look at the ratio of the 2 isotopes of, say, oxygen in the precipitation that fell and eventually formed that ice. And what do we do?